I'm Phillip. I'm a software engineer at Meta. Currently, I work in the React org, where I work on the native architecture supporting the React Native framework. This is a relatively technical talk. It's not about announcements or calls to action. It's for the curious ones that enjoy going under the hood of the frameworks that they work with. I hope you will leave this talk a little bit more enlightened as a developer, and that the knowledge that you gain from this talk will help you build more effective systems in the future. Cool. So in order to understand this talk, we first have to understand how the JS environment works. JavaScript cannot execute without a runtime environment. What does this runtime consist of? It has a JS engine. There are many JS engines out there that power different browsers. V8 is well known to power Chrome. The engine is responsible for the execution of JS code and handles memory management of values. Another fundamental thing the runtime provides are the APIs, such as those to manipulate the DOM. There are other concepts, such as queues and event loops, that are used to manage synchronization within the runtime. So let's go back to the conception of React Native about a decade ago. How did we integrate the JS runtime environment into a mobile one? We used a JavaScript engine called JSI, best known for powering Safari in Apple's ecosystem. This is a C-based API that allows us to embed JavaScript at runtime into our native runtime. So you guys know all about the React Native bridge, right? So this was the conception of the React Native bridge, where we would manage and communicate with JSI. Sorry, JSC. JSI is coming. So let's talk about the flow of data in this old world. All JS events would need to go through the bridge. The bridge would serialize the commands to JSON and invoke these methods in JSC. The callbacks would get asynchronously batched into a JSON response. We would then deserialize the response and invoke the method on the native module. So here, I have some sample code on how we would call the JavaScript error method in JSC. It consists of getting the runtime, getting the error method, and then invoking it with an argument. I'm not going to go through every detail here, but the reason it looks so verbose is because the JSC API is C. We have to manually manage memory ourselves, and C is always going to be syntactically heavy anytime we try to do something object-oriented. So this model works. It worked. But one of the biggest problems of this setup was the lack of flexibility. So first, C is challenging to work with. It's verbose, error-prone, and we had to manage memory ourselves. Next, everything has to go through the bridge. This is challenging for maintainability, as the bridge starts to get too many responsibilities. Finally, the implementation of React Native is tightly coupled with the JS engine of choice, JSC. We don't have the option of using another engine without rewriting the framework. So instead of coupling the architecture with a specific JS engine, what we want is an interface that gives us the flexibility to plug in any engine that we want. And also, we would like to avoid C and avoid having the bridge as a dependency for JS and native communication. So yeah, in this diagram, it's like, we want to be able to use V8, Hermes, or JSC whenever we want. So a few years later, engineers at Meta came up with JSI, a C++ interface for apps to embed JS, designed to be engine agnostic and lightweight. Instead of the native implementation being coupled with the engine, we would use an injected implementation of JSI. For example, Microsoft began supporting React Native's desktop environment with a JSI implementation of Chakra. At Meta, when we were limited by the capabilities of JSC, we decided to build our own JS runtime called Hermes. The JSI abstraction made it really easy for us to test changes by simply changing the dependency in React Native. Otherwise, we'd have to fork our code everywhere. So JSI can be considered a wrapper of the underlying engine's API, but because it's written in C++, there are some functional changes as well. The main functional change after integrating JSI is the flow of data. From native, we would call JSI, which can dispatch and invoke commands via C++. This is invoked into a C++ shared memory later because JSI is written in C++. The updates in memory will be reflected and visible in JavaScript. The way this works depends on the implementation of JSI. So JavaScript can immediately access the C++ layer, whereas before, it could only communicate to native by batching asynchronous calls to the bridge. So remember this, how we invoke the JavaScript error using JSC. This is how it looks with JSI. The JS runtime represents an object, is represented by an object with the type JSI runtime. We then retrieve the error method from the global property of the runtime and then invoke it. Because we're using C++, we don't have to handle marking objects for garbage collection ourselves. In my opinion, this code is much easier to read and write. So now we know the motivation and the high-level idea of why we use JSI. Let's look at what APIs JSI offers that allows us to power React Native. Cool. Let's start with the JSI runtime. Remember the diagram of the runtime I described in the beginning of the talk? JSI runtime is an abstraction of that. It's implemented with the JS engine of choice. This instance of JSI runtime is fundamental to using JSI. Its implementation determines how we read and write values to underlying memory and how we invoke JavaScript methods. It's highly advanced stuff. What you do need to know is that an instance of JSI runtime is a dependency for most JSI APIs to work. As I introduce other JSI types, I'll be going over more of these APIs. There are some things to know around using JSI runtime. It can only be read and written to from the JavaScript thread. Otherwise, you may retrieve incorrect values or trigger undefined behavior. In React Native, the framework is responsible for managing the lifecycle of the runtime. It can be torn down and restarted at any given time, which means that capturing it means that you have to manage the lifecycle yourself. Finally, the runtime needs to be passed to almost every single JSI method. This is intuitive when reading values from JavaScript, but we have to do this when creating values as well, because JSI will need to track the values in C++. The JSI runtime is not a singleton. In advanced use cases, we can handle multiple runtimes, and I'm pretty sure I saw some talks that did that today. The most fundamental type in JSI is JSI value. It's a C++ representation of JavaScript values. JSI value has a number of APIs to convert to permitted values or subclasses. In this example, we have an example of JSI representing a Boolean. We can convert it to a native Boolean, but trying to convert it to a string will throw an error. More practically, JSI value is what we pass to JSI to invoke JavaScript methods from native, and it's also representative of the values that we receive for JavaScript methods that return a value. So here we have JSI object. It's a subclass of JSI value that provides object APIs like property getters and setters. This example is not too interesting, but I'll get into the capabilities of object later. JSI also offers object representations of JS functions. Here, we retrieve the global promise function from the runtime. We then create an instance of this promise that lives in JS memory, but is created from native. This example shows how native can access functions from JavaScript, but what about the other way around? I also want to add that this is essentially what we do to support promises in native modules. Cool. So we can also embed native functions into the JS runtime with what we call host functions. In this example, we embed a native function called host function onto the JavaScript global property. We can then call this function off the JS global object. So this is an example of how JS can invoke something in native. Similarly, we can embed JSI objects into the runtime as host objects. Retrieving values on the object will trigger the get method, which can be overridden in our implementation of the host object. In this example, we override get to create a method called myMethodA on the host object. After installing the object onto the runtime, we can call myMethodA, and it will invoke the underlying implementation that we overrode in the get method. So you can see how powerful this pattern is, as we have a way to share objects between JS and native, where the user doesn't have to worry about any memory management. It's all handled by JSI. So Now we know how we can use JSI to communicate between JS and native. How do we actually use this API to power React Native? I'll share a few examples. So remember the pre-JSI native module communication flow? Let's revisit it real quickly. The bridge would invoke the JSI API to start some work on the JavaScript runtime. In the callback, the runtime would batch some serialized JSON response encoding the native module instructions. And then finally, the bridge would deserialize this response, look up the module, and then invoke the methods. So I'm going to share with you the native module flow when we first integrated JSI. When the runtime invokes the native module, it passes a JavaScript value to the underlying JS engine, where the JSI implementation will then track it in C++. This gets passed to our bound host function, so native call. Our host function would then convert the JSI value to a C++ dynamic. And so if you don't know what a C++ dynamic is, it's just a bag of values similar to JSI value, but it's not limited to representing JavaScript values. This standardized type would then get passed to the native module infra. And then the module infra would look at the native module, convert the arguments to native types, and then invoke the method. Note that here, we've decoupled the flow of data from the native bridge. So there's no bridge here anymore. In the new architecture for native modules, also known as TurboModules, we do things a little bit differently. Instead of using a host function, we used a host object. This example is iOS specific. We can leverage the toll-free C++ bridging in Objective-C, Objective-C++, and go directly from JSI value to the native type. This improves method invocation performance because we can save a deserialization pass. Cool. So let's talk about the rendering layer that powers the legacy architecture. So the path is very similar to the native module flow because we manage nodes with a native module called a UI manager. The native module infrastructure converts the dynamic to a general mapping of prop names to generic object types. There's additional work we have to do. We have to do an additional deserialization pass in order to convert the generic object types to types that can be recognized by native views. Cool. So in the new architecture, we use a host object instead of a native module to represent the UI manager, decoupling the critical path from native modules. The UI manager converts the JSI value to raw props, which is just a generic wrapper of JSI value. We don't do any conversion here. This is just a wrapper. Then, finally, we directly convert the raw props to native type props and pass it to a native view. So in this flow, we saved a number of deserialization steps. So these are some benchmarks on the new architecture renderer. It has noticeably improved rendering at scale, especially on iOS, where we can leverage toll-free C++ bridging with Objective-C++. But unfortunately, we still have some not as great wins on Android due to the serialization requirements of JNI to interface between Java land and C++. So this is just to show you that JSI is not some silver bullet that creates highly performant JavaScript apps. The API is really powerful, but it needs to be used thoughtfully. Cool. So now I've shared with you the main capabilities of JSI. I'm sure many of you are wondering, should I use JSI? If you're an application developer, my answer is probably no. For the most part, we've abstracted much of this away via the native components and native module API. Most product use cases will not require interfacing with the JavaScript runtime directly. If you're a framework developer, my answer is maybe. There are some advanced use cases with JS and native communication that can't be solved with React Native's current offering. There are actually some libraries leveraging JSI today. I'm pretty sure I saw some in the talks today. But I'd like to share one example that I think all of you are quite familiar with. Expo modules. So we're App.js. So Expo modules is unique, right, because it provides an expressive DSL that allows developers to create native modules in Swift and Kotlin. And Expo modules is able to achieve this using all of the concepts I talked about today, converting their DSL into custom bindings that allows you all to implement native modules in the most modern languages. So the React Native core team never made it official that JSI was available to use in consumer apps or libraries. It was through sheer ingenuity and curiosity that the community was able to figure out how to utilize JSI to build incredibly advanced features like Expo modules or vision camera. So this meant that they had to do some really hacky stuff, such as the example that I'm showing here. This is a common pattern that advanced libraries use to retrieve the JSI runtime on iOS. A private method is exposed off of the bridge. Then a hard cast is done to the runtime type, which is not possible to be caught during compile time if this cast was incorrect. They had to do this because our core infra was not initially set up to support other people using JSI. But I'm happy to announce that this year, we've been working on a proper set of APIs for developers to leverage JSI in their libraries and applications. So note that all of the APIs that we talked about today have a common dependency, JSI runtime. I'm reiterating this point because the APIs that React Native provides revolve around giving access to the JSI runtime. So the first API I'm going to share with you all is the host delegate. The host is a new architecture's abstraction for the runtime. It's responsible for creating and managing its lifecycle. The host delegate will receive a callback when the runtime is finished being created, so it's safe to access. This is also the earliest time you can safely access the runtime. Usually, the host delegate is the application, as the application is responsible for starting the React Native runtime. At Meta, we use this to bind application-specific logging functions that need to be ready as soon as JS execution starts. This is the iOS API, where the host will call did_initialize runtime when it finishes creating the runtime. In Android, the pattern is extremely similar, except we have to use JNI to execute C++. The main difference here is that the callback is injected rather than delegated because of the language boundary. The callback that's injected is called the bindings install function, which is provided by the delegate. Next, I'm going to talk about C++ TurboModules, an offering from the new architecture. The distinction from TurboModules and legacy modules is that a JavaScript spec is a source of truth of the model's shape. C++ TurboModules are also unique because every method will receive a reference to the runtime. We can do this because by default, C++ TurboModule methods are run on the JS thread. Just like any other native module method, we can invoke the method from JavaScript to execute the underlying code. If you wanted to install bindings to the runtime very early, you could potentially call it an index.js, where we mount the root component. Since it's written in C++, it's a naturally cross-platform solution for installing bindings. At the moment, the stable API for C++ TurboModule registration is in the app layer. We don't officially support auto-linking yet. However, in 0.74, we've introduced experimental APIs for C++ TurboModule auto-linking. Please check out this post in the new architecture working group if you're interested in these APIs. The last API I want to share with you is via TurboModules. We've introduced a hook that takes in a runtime argument. The native module infra will call this hook when creating the native module. Since native modules are initialized on the JS thread by default, this is thread safe. This does not require an app layer change. We just need the module to be linked. For iOS, we provide a protocol called RCT TurboModule with JSI bindings. This will enforce that this hook is implemented by your module at compile time. This is the Android API equivalent. Note that it's extremely similar to the host delegate. But here we can install bindings in the module layer instead of the app layer. These TurboModule APIs will be available as experimental APIs in 0.75. Now, all of these APIs are invoked in situations where you're already guaranteed to be on the JS thread. However, React Native is a multi-threaded environment. We have the JavaScript thread, obviously. We have a UI thread, which is a thread that can safely update UI components and retrieve information about the UI state. Finally, a fundamental native capability is to allow creation of arbitrary threads to execute work in parallel. What if we need to read or write values to the runtime when we are on one of these non-JS threads? We have an API for this use case called the call invoker. The call invoker provides an API where we can dispatch onto the JavaScript thread asynchronously. Currently, we do not support blocking the current thread to finish execution on the JS thread. The API is simple. You just pass in a Lambda to invoke async that takes in a reference to the runtime. In C++ TurboModules, getting the call invoker is easy. It's always passed as a dependency to the module. In iOS, we provide a protocol called RCT call invoker module. After conforming to this protocol, the native module infrastructure will decorate your native module with a property to access the runtime. On Android, we've made the call invoker available through the React context, which is injected to native modules and native components. Again, this must be passed down to a C++ layer via JNI to actually invoke the underlying logic. We've introduced these call invoker APIs in 0.75. These APIs are actually forward compatible, so if you're already using the call invoker, you don't have to fork your logic when migrating to the new architecture. Cool. So that's the talk. Hopefully you found that interesting. If you have any questions, Meta will be in the expert lounge after this talk. I want to say thanks to all these people here for supporting this work over the years. Many of them are here today. And then finally, I want to thank all the developers here. Thanks for keeping me employed. But also, it's such a privilege to support all of the amazing work that you guys do and being a small part of your industry journey. Thank you.